So chapter 7, first question. It's really easy, just have to derive. So for part A, I was holding a pen, anyways. For part A, just do individually, each one on its own. So y prime is 2x plus 1 plus the let me remove the plus. For the derivative of cosecant is minus, and then cosecant cotan. Let me put the x's. Cotan x. And then for ln, it's nothing but 1 over, and you have the derivative up. So like you could say not 1 over necessarily, the derivative over the function. And then this cancels, so your new thing here is 1 over x. So just replace this by that, like that. Simplest form. For this one, just y prime is same thing as up. It's derivative of here up, so derivative of this over square root of x. So this is gonna be derivative of that is gonna be 1 over 2 square root of x times 1 over square root of x, which is going to be 1 over 2x, pretty much. And that's it for first one. So to express this in a single function, ln function, with coefficient 1, which means that everything has to be inside the ln. So what we're going to do is we're going to use this rule where we take the coefficient and bring it up to be the exponent. Because ln is, you could think of it as linearizing a line. So this was actually x squared. It turned it into 2 ln x, which is something linearly graphed. It could be linearly graphed. And plus ln y cubed minus ln z to the power 5. And then just follow with the next rule. So this is just me simplifying. So this is equal to yeah, just join them using this rule where you just, the ones that add you multiply, the ones that minus you divide. So x squared, another way to think of it is to make this plus and this minus, so when you add them this will automatically go in the denominator. Just another way to think about it. So y cubic over z to the power of 5, and that's it. One coefficient, the entire expressions encapsulated here. Here it's the same thing as part 2, but it's the reverse. So let's do that. First let's simplify. So ln, let's do step by step. So a to the 3 and b to the 2 over 5. This is nothing but over, I mean it's the root. So root, the normal, let's say root, is going to be over 2. This is why squares leave, because 2 over 2 is 1. A over 1 over 5 here over c squared b cubed. Again, let's keep forward. These add up. It's going to be, well, 3 plus, that's how we're going to do 3 plus 1 over 5. It's going to be 16 over 5 times, I'm going to simplify this with this. Let's see which one. Oh, 3 is bigger down, so it's going to be down eventually if you want to keep the positive exponents. So 3 minus, no, yeah, 3 minus, because I'm bringing the other one down, 2 over 5. So 13 over 5. So I guess there's nothing here. So c squared b to the power of 13 over 5. If you want to keep it up there, it's fine, but either way we're going to split them this way. Ln this minus ln that minus ln this. So this is why I wanted to put down. Yeah, equals, now we're going to split ln a to the power of 16 over 5 minus, because it's down, ln c squared minus ln b to the power of 13 over 5 equals, just drop it down as easy as this, ln a minus 2 ln c minus 13 over 5 ln b. And yeah, we're done. So here you have to find the factors. So if you don't have a calculator that will do it for you and you're just thinking, just split it, like obviously what's here, 2, blah blah blah, and you just keep on going. But I'm not going to go through this process, not to waste your time. You will eventually end up with, I believe, 32 and 81. Yeah, 32 and 81, they're the best because you want to get them in terms of 2 and 3. So they're made up of 2's and 3's. So 32 and 81. 81 is nothing but made up of 3 to the power 4, because it's 9 times 9, and each 9 is 3, 2 with 3's. And this one's 2 to the 5. So we can already see that this number, if we break it down step by step, is nothing but the ln of the multiplication of the two numbers. And just like the previous exercises, we've seen that we can split it. So ln 32 plus ln 81, and then just do the exponents, where you just 2 to the power 5, bring it down, it's going to be here, plus ln 3 to the power 4, bring it down, so you get here. And yeah, that's it pretty much. Okay, so first things first, find the domain, and you could say the range, but the range of ln in all cases, if not most cases, I mean, it's gonna look like this otherwise, so it's gonna be plus infinity. This is gonna keep on going, keep on going, keep on going, even though it kind of like is lessening, but realistically it's just gonna go, even if it's less and less and less and less, it's still gonna keep on going. So yeah, so the domain is gonna be whatever is inside is greater than 0. So 1 plus x greater than 0, so x is greater than minus 1. It can never break this rule. It's strictly greater than, it cannot be minus 1. If it is, which is the second step, what if x approaches minus 1? What does y become? What is y approaching? Or the function itself. You can also write it like that. For me, I'm going to write y. Y approaches minus infinity. That's the thing. It approaches minus infinity all the way down. So, yeah. And what if x approaches, we cannot do minus infinity because we only have greater than 0. So this is our lower boundary, you could say. We cannot go minus infinity. This is our lowest. So we can go plus infinity instead. So what does y reach? As you said, it just keeps on going, so plus infinity. And yeah, so this gives us out that this is a vertical asymptote, a value that we cannot reach. We're just approaching, but we can never reach. We don't want to reach it. Doesn't even like touch it, just approaches. Anyways, yeah, so this helps us with the shape. We know that we have a function with a vertical asymptote. I mean, if you want, we can build on the graph step by step, so that you can see the point of these steps, like what's the purpose of doing each step. So first of all, we know that we cannot exceed a certain point. Second of all, we know that at this point there's a vertical asymptote, x equals to minus 1. So we know the graph is going like this. We know it's approaching here, and we know that it's going to increase somewhere. So this is like kind of like the tips these points give you. Next step, you can find the y prime. Y double prime I think is optional, but it's fine if you want to do it. Lns are easy. Lns, yeah. So this is the y prime, just instantly like this. Derivative of this is 1, so it doesn't matter, it doesn't affect, so 1. Y double prime is, again, you don't have to do quotient rule, it's just bringing this up to be this, minus 1, and just do chain rule. So it's going to be square down, but you can do quotient rule, but if you want to do this faster, you can do it normally like this. And drop the minus, so minus. Yeah, so this is y double prime. Now let's look at the signs. Let's observe the signs and how this function reacts. So we said we can only be greater than 0. So let's check when, I mean, there are two ways to do this, because I know this, I can deduce something here, but if I deduce something here, I can know something else. But anyway, so if we look here, and we can notice that knowing that x can only be greater than minus 1, if we pick minus 1 here, we'll get 0. And we know that it must be greater than minus 1. So if it's greater than, if it's something like minus 0.999, it's going to be a positive here. So it's going to be always positive, always greater than 0, always greater than 0 for all x greater than minus 1. It will always be greater than 0, because that's our defined domain. And if you try that, it's always going to be 0. So it's always increasing. It's always increasing, but that's just predicting. So we're going to do that step by step. So double prime here, this is always positive, but there's a minus, so it's going to be always negative for no matter what value you give it. But because we're constricted with this, so we can say for all the domain we have, which is greater than minus 1. We've done those. Now we can do the table. I mean, to be honest, you don't have to do it as a table, I think, but it's fine. Special values. Ones with e. To be honest, you can keep on going with the e's. You can do 1 over e squared. It doesn't have to be 1 over e, and you just keep on going. They're really easy with the e's, because lin, you know, specially made for the e. Yeah. So this is like, you can do the y prime or stuff, but I'm just gonna do the what do you call it, like what is the value? So for example, 1 over e. If you put 1 over e, what do you get? It's actually, in this case, it's not 1 over e, because the graph is shifted to the left. So normally it will be 1 over e, giving you -1, but here it's shifted to the left, so -1, shifted with it, so it becomes -1, and 0, because 1, actually, ln of 1 gives you 0, but here it's not 1, it's going to be 1 plus 1. So if you want it to be 1, if you want the inside, x plus 1, to be 1, x must be, okay, this is annoying, x must be 0. As you can see, this is why I'm saying it's shifted. Try that with 1 over e. How can you get x plus 1 to be 1 over e? You have to subtract the -1. You have to subtract the 1, so it's going to be -1. X equals to -1. 1 over e -1. So yeah, here same thing. It's e, but then you subtract by 1 again. So yeah, so this gives you the famous trio 0 and 1. This just help you determine how the graph looks like. And yeah, we've got our points. This is our x, this is our y. We know how this function reacts, we know how it looks like, so we can just graph immediately. The points that we need to plot, 1 over e -1. I mean, if you were to approximate that, 1 over e, too heavy, I'm just going to do e -1, -1, -0.6, so it's technically, if this is 0.5 somewhere here, to give you a -1, something like here, and this is here 0, give you 0, and then e -1, which I think 1.7, so if we pick this to be 0.5, 0.5, 1, 2, this is somewhere around 0.7, it's to be 1, yeah, somewhere here. Yes, it doesn't have to be as accurate, and I'm like graphing literally digitally, so it's going to be super weird. But yeah, it generally looks like this kind of thing, this kind of graph, this kind of thing. So yeah. For number 6, graphing could help, but let's do this first. There are 2 steps that we need to do. First of all, determine the domain, because the domain can restrict your final answer. Your final answer could be something possibly larger than the actual domain, or what you can actually have as an answer for this, because your domain can restrict, I mean, in this case, ln restricts the inside, as an input, or the domain, it restricts numbers that aren't positive. So 0 is wrong, it's going to give you undefined, and negative, same thing. So let's do that first. So 1 minus 2x over x minus 1 greater than 0. That's the domain inside, not the function. The function, we're said that it's greater than or equal to 0. We're solving for x, but we're doing the inside for now. Yeah, with this you can do this using a graph, but first, if you want, you can find the points. You're free to do whatever at which. So for the points first, here it's 1 is this 0, 1 minus 2x, x is others. Okay, we can do this, equals to 2x, and then divide to half. Yeah, this is going to give you 0. For the other one, it's going to be x is 1. So we could have an interval less than half, greater than 1, between the two, so on and so forth. So let's find that out. One way you could do this, if you want to fix this, okay, so let's say this is 1, 2, 3, 4, 5. This can help you get an idea on what's really happening in that condition, and determine whether it's between, greater than, something else, less than. So yeah, So let's grab them one by one. So 1 minus 2x quickly. 1 here, it's 1, always the y-intercept is the easiest. Minus 2, it's going down and at a factor of 2, so not like the normal x where you go from point to point to point to point, no, a bit faster. So a half, a point, a half, a point, a half. I'm doing it like this, a half, so something like that. I'm only concerned with, yeah, I already have a point from 0, so that's fine. I don't have to extend here because I already have a half, slightly, I mean I can do it a bit. So a half, no, a half, yeah, and point, and so on. So a line would be like this, say from this point to this point. I think it messed up terribly. Wait, I might have done the mistake. Anyways, I think it's the line. Let's try. Yeah, it's the line approximation thing. Anyways, so it's gonna be like this. It's also my plot slightly. So this is the first one. Again, I'm supposed to do this quickly, but again, digital issues and stuff. So x minus 1. Minus 1 is down. X is 1 point, 1 point, 1 point, like at slope of 1. If you want to do 1 point behind, when is it greater than 0? When either of those are positive, it's going to be greater than 0, or both of them are negative. If one is positive, one's negative, that's instantly a negative number. So when they're both positive, which does not happen, because either one is up, as you can see, either one's up, or the others when the other is down, or you know, the other one's up when the other one's down. However, we have the region of negatives when they're both negative. This region, the one right here, starting from here all the way to here, this region, I mean, it's here, this is the point, so from here to here, this region is actually our solution for this part. So it's from this half to all the way inside the all the way to 1. So it's actually between. So it's half, and is it strictly? Yeah, it's strictly less than greater than 1. So it's going to be between those two. Yeah. So this is how we do it for sure. Let's erase this. Now we got our restrictive domain. So let's do the ln. Now this is the expression itself we're given, right? Nothing changed. X minus 1 greater than or equal to 0. This means that if you do substitute the ln, so for example, I mean, wait, I'll show you right now. 2x over x minus 1. 0 could be expressed as ln in the form of ln. So ln 1 is 0. So there you could equate the lns. X minus 1 greater than or equal to 1. Take 1 to the other side, 1 minus 2x over x minus 1 minus 1 greater than or equal to 0. Now we can make this into a numerator and a denominator, so x minus 1 over x minus 1, like that. So I did it in a single step so that I don't have to do it again. Actually, yeah. Yeah, so minus 2x minus x, so minus 3x. And here minus 1, so plus 1, so 2 over denominators greater than 0. You can do this again quickly just to discover, is it between or is it not. To be honest, at this point you have a negatively sloping line, a positively sloping line. I don't care how their slopes are oriented, but it's like that. So if you do indeed have a solution, which if you try finding the points, 3x equals to 0, x equals to, take that to the other side, divide by 2, so 2 over 3, and x equals to 1. By the way, one way to find this other than graphing is to find how the functions are behaving. So for example, you derive increasing, decreasing and stuff, I think, yeah, and then find when it's positive and stuff. So yeah, if you do graph this, you're gonna get the same area, same region, not same as it's actually smaller, I believe. Yeah, it's smaller, and this is why we actually end up picking this, you know, the region I said within. So like it's gonna be like this, actually on it. So it's gonna be somewhere here, and it's gonna be like this, something like that. The region where they actually are, you know, touching and stuff, and they're both negative. So this is why you get 2/3 less than or equal to x less than or equal to 1, because it's not strictly here. It's greater than or equal to. So I mean, the equal to is what I care about. So this is why I put the equal to here. Yeah, I might have rushed here a bit, but I just wanted to show you that if you do graph, and I can't really control this well, but if you do graph, you're gonna end up with that. Again, there are other methods. This is just the way I use it, the way I do it, the way I use. So yeah. And this is where when you decide this, you look back at your domain. 2/3. If you want, you can use this all the way, where you go like, this is half. Get the smallest value. Smallest value is half. Get the largest value. The largest value is 1. So it's gonna be between those, right? This is what this is saying, and this is saying there are 2/3 is somewhere here. Yeah, somewhere here. Anyways, no, I think it's slightly here. Anyways, it doesn't matter. Let's just put it here. So it's going to be this, including this. This is the domain that restricts you, and you cannot have it equal to. So your solution set is going to eventually be this, and so this is why you slash this out, and that's your new solution. Okay, so number 7. These ones are fairly easy, so let's do them immediately. You can take 1/3 out, so 1/3 integral from 1 to 2 1/x times dx, and then this immediately becomes 1/3. This is ln absolute value of x from 1 to 2, which is evidently ln 2/1, because it's ln 2 minus ln 1, so you can say ln 2/1, so ln 2. You can put it inside, keep it outside, either are fine. And then b. For b, if you derive without like a faster way than doing let you, but if you're fast enough, then for sure. This is 2x plus 2 if you derive. So we want this to be that, so we multiply by 2 here, of course, the entire expression. So this becomes 2. But then because we multiply by 2, we have to divide by 2 outside, so that they cancel eventually. So half integral, I mean, no need that, they're already, this is the derivative of that, so I can immediately say ln absolute value of x squared plus 2x from 3 to 5, from 3 to 5. So half ln, I'm gonna do the same as the previous one. I'm gonna divide immediately, put this answer, divide over this answer. So 5 squared, that gives you 25. 25 plus 2 times 5, that's 35. 25 plus 10. 3 here, 9 plus 6, that's 15. Cancel these, 5, 5, 7, 3. Yeah, so you get half ln 7/3. Put it inside, put the half inside, keep it outside, it's fine. If they want just to ln something, then you know what to do. Put the square root, and yeah. So yeah. So now for cotan. Cotan, that's basically cosine x over sine x dx. And then this way, if you notice, the derive sign, you get cosine, so you have already the derivative. So ln instantly of sine of x, and of course, because it's indefinite, you don't have boundaries, limits, upper bound, lower bound, whatever you want to call them. So this is your answer with plus c. And sine can be written as 1 over sine, however, to the power of minus 1. This will flip this back to sine. All I did was flip it and say that I want to flip it back, minus 1. So if you distribute, it's going to flip it back to sine. So, and 1 over sine is nothing but cosecant. So I can say step by step, ln cosecant minus 1 yeah, plus c. Now take the minus 1 out, so it becomes minus ln absolute value of cosecant x, of course, cosecant x sine x plus c. And yeah, two answers. For multiple, of course, we're talking about multiple. For written, stopping here is perfectly fine. I mean, this is more simpler than this, to be honest, but for multiple, yeah. So for number 9, you have really two ways to do this. You can derive like this, and then, you know, quotient rule, and then quotient rule, you're gonna do product rule for this one. It's slightly a mess because you're doing them all at once. So if you can't, you know, plan this step by step, then you get them wrong. So let's do this ln, using ln. Ln's easier. So ln y equals, we're operating ln on both sides, so it's completely fine. They're equivalent. So ln of this, because this is over this over that, ln of something, where you have this over that, you can split them into ln that minus ln this. So I'm going to split them immediately, save time and steps. So x to the power of 2 over 3 times, we're doing again two step by step, squared x minus ln of square root, I'm going to write it as power half, and this is again ln, split them 2 over 3, products will add with ln, tan, I'm gonna keep the power outside, same thing here, 2 over 3, so that I can bring it down immediately in an obvious way, so that it's noticeable. I can bring down the power, I already have it, so ln 1 plus 1 over x squared. You cannot split these two because they're not products or the divisors, or, you know, you're not dividing them, you're not multiplying them, you're just adding them. Same thing with subtraction, you don't do it. So yeah, let's bring down the power, 2 over 3 ln of x plus 2 ln tan of x minus half ln 1 plus 1 over x squared. We did not derive yet. This is nothing but equal to ln y, right? So I just wrote it back again so that we can see it. So let's derive now. So it's going to be y prime over y, because that's how ln works. When you derive it, you bring it back to its original form, which is y prime over y equals 2 over 3, this is nothing but 1 over x, plus this is nothing but its derivative, which is 1 over itself. Its derivative of tan is nothing but secant squared x over tan itself. We can simplify that, of course, because we have a sine here, and cosine, and we have a cosine over here, because they're both cosines. This is, you know, 1 over cosine. Anyways, minus half times, deriving this is going to give you nothing up, but this 1 over x, yeah, this is going to give you minus 2 over, I can write it up, minus 2 over x to the power of 3. That's its derivative up, because this gives you 0 and this gives you minus 2, because you bring it down minus 2 and then add 1 here. And this is plus 1 plus over x squared. And yeah, so you can simplify here, but I'm going to immediately jump to y. Let's substitute y. But again, you're not responsible to simplify any further other than maybe this, but that's it pretty much. You just write the term itself. That's y, by the way. All I did is multiply y here, because y prime over y equals this. So y prime equals y times that. So I'm just writing y. 1 plus x squared. Yeah. So I just wrote y times whatever we had, which, if you want to simplify, 2 over 3x plus secant is nothing but 1 over cosine. And this is cosine squared, because you have secant squared. And tan is nothing but sine over cosine, but we have 1 over tan, so we have cosine over sine, because it's opposite of tan, because 1 over tan. And yeah, cosine can cancel, so actually you have 1 over sine times cosine. Yeah. Oh, you have a 2 here, so you can write that out. Minus, technically, yeah, you could simplify this can bring down the x cubed. But anyways, like, this is just math. All that's left is just math, basically. So yeah. Okay, so let's do the inverses. They're really nice, they're easy, and yeah, step by step they kind of like get a bit technical, but let's start with the first ones. They're easy. So f prime of x, we want to find that, not prime, sorry, inverse. Okay, so what we do, I mean, there are two ways, and they're both the same. You can either switch at the beginning and then solve for, if you switch, you can solve for y, or you just solve for x and then switch. They're the same. I'm going to do the other one, the last one, which is solve for x and then switch. It's the same. It's the same. So y equals minus 6 x plus 1. I'm going to solve for x. So y minus 1 equals minus 6x. Minus is going to swap. So 1 minus y over 6 equals to x. Interchange. So y equals 1 minus x over 6. And you're done. You want to divide by 6, it's fine. 1 over 6 minus 1 over 6x will give you the same answer. And for b, you're just gonna have to, again, let's write it out, minus 4x plus 1 over 3x plus 7. And then multiply. You can either interchange or, you know, they're all the same. So y into, let's write it out immediately, 3xy, if you want to do it by order, 3xy plus 7y equals minus 4x plus 1, and we're solving for x again, right? We're solving for x. So we want to group the x's together, so 3xy minus 4. Also, if you feel like this is confusing you because you're used to y or x, or it depends on your way, just do your way. As long as you're doing the same steps, it's fine. Like, if you're interchanging then solving for y, it's the same as solving for x and interchanging. So yeah, so plus 4x equals 1 minus 7y, and then factor out x, so 3y plus 4 equals 1 minus 7y, and yeah, we're just gonna divide, so 1 minus 7y over 3y plus 4, and so interchange. You're gonna end up with y equals 1 minus 7x over 3x plus 4. I don't think anyone faces a problem with this one, and if you did, I hope this helped. Okay, so let's find the inverse of this. So y equals 2 plus, usually every single inverse they give you, it's super easy, so don't be intimidated by anything you really find. There's always something for it. 2 plus, yeah, let's solve for x. So y minus 2 equals 3 over x cubed, and then just take it to the other side, so x cubed into y minus 2 equals 3, divide x cubed equals 3 over y minus 2, then cubic root of that, so x equals cubic root of 3 over the cubic, well, I can cube root everything, cubic root of the entire expression, 3 over y minus 2, and then interchange. And yep, we're done. Also before that, you do have conditions. So for example, for the previous ones, this one I don't think you had any condition. This one, I think you ended up with something like 3x plus 4 down. If you ended up with 3x plus 4 down for this one, your condition is going to be that this is not equal to 0. So your x is going to be not equal to minus 4 over 3. So write that condition if it's written. Here, same thing, x cannot be 2. And yeah, that should do it. It's cubic root, so you don't have to consider the sign. If it's an even root, square root, quadratic root, or whatever it's called, and so on and so forth, you're gonna have to consider the sign. So you're gonna have to find this function to be positive. But in this case, no, it's cubic root, so everything's killed. Anyways. Okay, so for this one, let's start by writing it out. It might require a bit of extra thinking maybe than the other exercises, maybe, who knows. So what we're gonna do, we're gonna try completing the square for this one, because we want to isolate x in a way. We want one x, not two x's, not with different powers, so we can't really factor out anything. Even if you try factoring out the x here, you're going to be left with an expression and you can't immediately solve. So complete the square. This minus annoys me, so I'm going to take it out. So minus into x squared minus, put it back in, becomes plus. So just to show you that it's the same, I did not change anything. And I'm going to do a certain move, which is the completing the square move. So if you want, not to confuse you, I'm going to extend this parentheses because I was going to do something. So let's extend this parentheses. And okay, now what we're going to do is we're going to divide by 2. Just to show you, just to get the expression here, divide by 2, you get 3 over 2, right? And this will always be plus. Whether this is minus, whether this is plus, this is going to always be plus. However, square this. Because what we want to take is to take the squares. So take x minus 3 over 2, all of it squared. Now, when you did this, you played around with the equation. So get it back to its original shape, or, you know, mathematical. Anyways, so we're going to subtract by the same value. The step I was going to do is I was going to take it out immediately. So I did that step by step. So y equals minus. Now, I'm going to, okay, step by step. Let's not rush things if you want. Plus 3 over 2 squared. I'm going to take this out. There's a minus, it will become a plus. Again, I'm doing this step by step. No rushing. Actually, let's square immediately. So 9 over 4 minus 2. Nothing special, nothing new. So y equals minus, now we can do this immediately, minus 3 over 2. Again, I get the minus from the middle term, nothing else. And take the x, take the number that's squared, and yeah. Now simplify this. Let me get my calculator. 9 over 4 minus 2 is nothing but 1 over 4. So plus 1 over 4. Now you can see that we have 1x. So we can solve for x. So y minus 1 over 4 equals minus x minus 3 over 2 squared. And then divide by minus. So 1 over 4 minus y. And then square root. So plus or minus this equals to x minus 3 over 2. I just put the minus, 1 over 4 minus y. I did the square root, and I got this. And yeah, x equals 3 over 2 plus or minus the square root of 1 over 4 minus y. Now, time to decide, plus or minus. This is where the condition comes in. X is less than or equal to 3 over 2. Now, good thing is that we can see clearly that there is a 3 over 2 here. So for it to be less than 3 over 2, do we add a number or do we subtract the number for the x to be less than 3 over 2? So for the x to be less than 3 over 2, we're gonna subtract, right? We're gonna subtract. We want it to diminish. So 3 over 2 minus this 1 over 4 minus y, and then interchange. And boom, we're done. 1 over 4 minus y. This is your expression. Let me quickly double check. And yeah, pretty much. So for number 6, we're going to use this rule. We're actually going to verify the rule. In number 5, we're going to use it. The rule says that the derivative of the inverse at the ordinate is nothing but the reciprocal 1 over the derivative of the function at the abscissa. So let's verify this. First, let's do the function, I guess. Derivative of the function. So g prime of x, let's derive. Instantly, you'll get x plus 1 squared minus. How do I do it so quickly? You can do this. X plus 1 minus 1, which is the function. I did nothing but take it up, right? How do you derive? Subtract by 1. So you get minus 2. Bring down the step by step. If you bring down the minus 1, so minus, you subtract by 1, so you get 2, and multiply by the derivative, so which is 1 basically. And this is no longer minus because I just showed you that I flipped it. Up is going to be minus 2, down is going to be 2. So yeah. Anyways, if this confuses you, just do it your way normally. Chain rule, quotient rule. I mean, quotient here is a waste, but you can do quotient rule if you're unsure. So yeah, let's keep on going. Let's substitute, or like this, or anyways. So g prime at 0, because that's what we want. For the normal function, it's the abscissa. So g prime of 0, put that in, you get minus 1. 0 plus 1, 1. 1 squared 1. 1 over 1, 1 minus 1. So yeah. And now g inverse. So step by step, y equals 1 over x plus 1. And so cross multiply yx plus y equals 1. And so x equals, take y to the other side, 1 minus y and divide by y. So 1 minus y over y. Interchange, y equals 1 minus x over x. Now derive, y prime equals quotient rule. For those of you who forgot, if you have a function with u over v, the prime of that is going to be u prime v minus v prime u over v squared. Order matters because this is subtraction. For the product rule, it does not matter if it's, you know, u prime times v plus v prime times u or the opposite. It's addition when you derive. So yeah. So let's derive this. That's minus into the function minus the derivative of this, which is 1, times the function, and this is squared. And yeah, so minus x step by step, minus x, this is nothing but 1, so I'm gonna ignore it. Minus 1 plus x, distributed the minus carefully, these cancel, so you're gonna get, to simplify, yeah, so you're gonna get minus 1, yeah, okay, so minus 1 over x squared, a simple equation. So for this one, again, substitute the ordinate, which is 1. So put 1, you get minus 1. Like g inverse prime, I guess, g inverse prime is nothing of 1. This is so weird. Of 1 equals minus 1, which is equal to that. Hence proved. QED. Done. And as ignore this chart. For number 4 we proved it, so number 5 we can use it. And find this. Rather than doing the inverse, deriving, we can just instantly use the normal, the other side of the function, which is 1 over the derivative of the function, no need for the inverse, the function at x equals to the real x that you put inside the function, which gives you the ordinate. But this is the inverse, so this is why I refer to it as x. All functions have x, even inverses, but they refer to it in a different notation. So yeah, so we're gonna find this. This is this. They're equal. So what do we first derive? So h prime of x equals 4x cubed minus 9x squared. We're gonna wait for this. Anyways, substitute. So prime, put 2 here. You're gonna put 4 2 cubed minus 9 2 squared. Let's do this instantly. 4 times 2 to the power of 3 minus 9 times 2 to the power of 2. You're gonna get minus 4. And so it's just 1 over minus 4. This entire thing is minus 1 over minus 4, or minus 1 over 4, which is, all I did was just 1 over. So yeah, that's it pretty much. So again, these are easy questions. Always the beginning has easy questions. So ln with e, instantly without thinking, there's nothing but the 3x, because ln is log base e and it's gonna eat the e away, you could say, so you're gonna be left with the 3x. Here you want the ln instantly, so you put this here. So this is nothing but e ln square root of x to the power of 3. Now we can eat, these two will be eaten. You're gonna have this. And here again, you can see them straight, not like this one. This one you had to simplify, otherwise it's not gonna be the same answer. As you can see, it's not 3 square root of x. You have to do stuff. Here, it's, again, like that one, it's instant. They're close to each other, so they're actually in front of each other. So yeah, so sine x instantly over cosine equals tan. Boom, done. Okay, so let's solve this. I mean, there are multiple ways to do this. There are really like infinite number of ways to do multiple questions. So for this one, let's group things up. So e to the x plus y, when you multiply things with the same base, their exponents add, equals 3. And here, we're going to use the ln property. So you're going to have x over y equals ln 3 over 2. Now let's progress. The e, you can technically get these to be in e and solve, but I guess the easiest way is just to bring down everything that we don't like. So the e, we can take care of it by using ln. Ln of this is nothing but ln 3, so things are really easy if we use ln. Because pay attention, if this is x or something, things might get harder. So, but this is 3. So ln e, immediately get cancelled out, x plus y equals ln 3. And this one, you can operate e. So e to the power of cancels with ln. So you have x over y equals 3 over 2. So let's do that. So this is nothing but x plus y. I did ln, so ln 3. And this one I did e, so x over y equals 3 over 2. Now this is nothing but substitution. You want to do linear combination, whatever they call it, and yeah, I'm gonna do substitution because I have over here. Like, I mean, I can do minus but anyway, substitution. So I'm gonna use this one. So x equals 3y over 2. Put that here. So 3 over 2 y plus y equals ln 3. So this is 5 over 2. 2 over 2 plus 3 over 2. So 5 over 2 y equals ln 3. So y is nothing but 2 over 5 ln 3. They're all numbers. Even though we have ln here, it's ln of 3. So they're all numbers. So you can substitute immediately. You got y. So x is nothing but 3 over 2 times that. Ln of 3. And yeah, 2 cancels. Now you get 3 over 5 ln 3. They bluntly just threw the equations. They never asked for a question, just solve. So you can either say y is equal to this, x equals that, or if you look at the solution, they just group them up in a point. You know what to do. Once you have the answers, it's super easy to answer in the computer or multiple on the bubble sheet or something. So yeah. Okay, so for this one, I didn't have time to go over the proofs, so sorry for this one. I can't really explain, but I can explain C actually, which is good enough, I guess. So I can't explain how they suddenly started using E into compound interest. I mean, it does work because it's exponential. E is nothing but a factor, and there's a proof for it, but again, that's what I said. I didn't have time to check. However, it is nothing, no conditions. I mean, I think there are no conditions. Maybe it's just the word continuous with working with limits and stuff, which actually was there part of the proof. So probably it's the word continuous. But this is indeed equal to, probably again with this condition, equal to p into 1 plus, which is what we are familiar with. Again, r is a number. If you want to use the percentage, yeah, percentage. Otherwise, just use it as the ratio. But yeah, percentage, so that you get 0.08. To the power of t. These are equal. So yeah, A, find the amount. So A equals, we're going to be using, of course, this one. So A equals P, which is 25,000, into e to the power of 0.08 times t, which is 8. Yeah. If you do this, you're going to get around 47,412, I believe. Anyways, it's math, so one number off, it doesn't matter. It's just plugging in numbers. How long does it take? Blah blah. So triple. So our final, you can think of this as P, and this is P0, initial and final. So this is final, this is initial. So 3P equals P e to the power of same R, 0.08. We don't know T. PP cancels. Ln, operate ln. So ln 3 equals, I did that to get rid of the e, and here we had a number, so no issue. T equals, I believe, 13.7 if you do the division, something around that. Again, numbers, doesn't matter. Find the effective rate. Now for this one, you can use the fact that they're equal. So let me show you how you can actually, technically, I'm gonna keep this as R, knowing that the way we wrote R here is, as you can see, as a ratio. As a ratio. This is actually 1 over, or like over 100. So it's a ratio. This, if you put the percentage. So actually, let's keep this as, for consistency, let's keep this as R. Ratio, ratio. We're not putting percentage. We're not putting percentage. So just to make my derivation easier, T equals P E R T. Cancel P with P. So let me show you this one thing. It might not be obvious, so I'm gonna try making it as obvious as possible. So E to the power of R to the power of T. I did nothing. I just took this exponent higher just to show you that these will multiply eventually to give you this. But yeah, with the same exponent, if you have the same exponent, you should have the same. So these should be equal. How? If you do the T root or whatever you want to call it, you're gonna end up with this basically. So cancel the T's altogether. Cancel the T's because same exponent. So you should have the same base. They should be equal. So yeah. We don't have R, so we're gonna look for it, right? Or no? Yeah, we're gonna look for R. So it's gonna be 1. R equals, this is the effective, by the way, this is the effective. This is E. Yeah, they're not the same. They're not the same. So RE equals E, you can call it, I don't know, R initial or whatever you want to call it, minus 1. And then try the numbers. E is nothing but 2.7 something, you know, in the calculator. And then R is 0.08. And then minus 1. Try that. I'll do it right now. E to the power of 0.08 minus 1. I get some decimal. I get 0.0833, which if you want as percentages, it's 8.33%. Check the answer in the solution. You should get the same answer because this is mathematically correct. So apparently the ratios are slightly different. It's again probably this word continuously made limits and stuff, made them different. So yeah, that's how we do it. You can do it with the way the solution does it, my way, any way you want. I just gave you options and choices. So for this one, let's do these ones. So y prime is nothing but the derivative. If you distribute, you get 3x minus 15. Derivative of that either way is 3. So 3 e to the 3x minus 5. And yeah, that's it. You can distribute, you can keep it. That's the same thing. So y prime is nothing but, minus 5, the fifth root of x, the prime of that, the derivative, just like how we did this one. The derivative of this, bring it down, e to the minus fifth root of x. Minus is down, it's not here. Yeah. So let me write it here. So this equals, let's do the derivative of this. The derivative of this, this itself is nothing but minus x to the power of 1 over 5. And so the derivative would be minus, bring down the exponent, and you're going to have 1 over times 1 over, and this is going to be x to the power of 4 over 5. So the fifth root of this. So let me rewrite it. So you're going to have 1 over 5 fifth root of x to the power of 4. 5 times this. So let's write that. So minus 5 times, oh no, minus 5 down, right? So yeah, minus 1 over 5 times fifth root, because there's so many 5s, so it will confuse you, x to the power of 4 times e to the power of minus, as we said here, fifth root of x. Now for c, if you derive, you're gonna have two functions. So if you want to derive, you're gonna have to use the, what do you call it, the product rule. It's a must. x is a function and you cannot discard it. I mean, here there is a function technically which is y, but this is why, I mean, derivative of 1 is nothing but 0, so the entire rest of the expression in the product rule is going to get cancelled. So here you're going to have to account for it. Derivative of this is 1 times the function itself plus the derivative, this stays the same, but the derivative of this now, which is what we have kind of like been practicing for, the e to the something. So bring down the derivative, so cosine, derivative of that is minus sine, so minus sine times e to the cosine x, and yeah, you can just do this. You can factor out, by the way, e to the cosine. Here we're left with the, here we have 1, here we have minus x sine x, and yeah, that's it pretty much. Okay, so graphing, again, don't be intimidated by anything graphs, don't have to memorize stuff in specifically, but it's just some steps that you might, like, if you feel like you need them, then they're probably what you need to write. So first of all, domain range, the basics, you should know them. Domain range, like you should have them in your mind, I mean, when you want to graph. This should be your number one, always your number one. So domain range, domain, e to the x, not everything and anything. Minus doesn't change that fact. Minus 1 doesn't affect anything. So you have r. You're gonna still have r. So range. This is where you can do the, I don't know what you call this way, but I'm just gonna call it reverse engineering. You're gonna get it back again. So e to the x is always positive. You know that, like this, asymptotic and blah blah. So always positive. Now what if I do minus 1? I did nothing but shift, either to the right or to the left. It doesn't matter to me at this point, but I'm just having a positive value. It doesn't matter for the range. Maybe it matters for the shape, but either way I can figure that out from the rest of the values. So minus, I multiplied by a minus. Multiplying by a negative or dividing by a negative swaps the inequality. And then we're gonna subtract. Minus 1 down, minus 1. So no, the function is nothing but less than 1, so on. Let me double check something. Okay, I just wanted to check if my mic is connected properly. So why is less than minus 1? You can write it the I don't know, the fancy way you could say, where you say r belongs to minus, no, plus infinity, no, minus, yeah, it's always negative, so minus infinity till minus 1. Or if you want to do it the other way, because we usually, I think mathematicians usually just write the bigger one to the smaller one, so minus 1 till minus infinity, same thing. It's just positive first. That's how they usually have seen them write it as. So yeah. Next step, behavior of the function. So do the infinities. So plus infinity. Here I'm free to do whatever I want with the axis because our domains are. Otherwise, if we're restricted, we have to use the restricted domain. So let's observe, let's place infinities. They're fun. Just put the infinity. Infinity minus 1 destroys it. It becomes infinity. E to the infinity destroys it. Infinity. Minus that, which becomes minus infinity, minus 1, minus infinity. So minus infinity. It's really fun to just put the infinity and see how it works. So x approaches minus infinity. Let's place that out. So minus infinity minus 1 minus infinity, e to the minus infinity is nothing but 1 over e to the infinity, which is going to eventually approach 0 because this approaches plus infinity or infinity, and 1 over that is nothing but 0. So this is 0. So minus 0, 0, minus 1, so you get minus 1. So y approaches minus 1. Once an x or an y approaches a value, if it's the x, is going to be a vertical asymptote. If it's the y, it's going to be a horizontal asymptote. And so we've just found our horizontal asymptote. And yeah. Third, I mean, you could say this is 2, this is 3. Derivatives. I mean, technically third and fourth. I mean, if you consider the y double prime to be another one and so on and so forth. Anyways, so y prime. Derive this. We have a its derivative of the derivative of x minus 1 is nothing but 1, so you can just say minus e to the x minus 1, and then the minus 1, its derivative is 0. So, and then double prime is just this, doesn't change because derivative of e to the something, you just put down the derivative. So again, you're left with the same expression 1, and yeah. This is always less than 0, because this is always positive. With a minus, it becomes always negative. Always positive with a minus becomes always negative. So this first one tells us it's always negative. Second one tells us it's always concave down. So as a function, it's concave down. And yeah. Fourth thing, they're left with the, you basically left with the, I mean, I think the fourth could be like a table of, you know, variation and stuff, but I really don't need for e to the x. It's super easy. 5 is y-intercept and stuff, x-intercept. I'm not gonna be bothered to do y-intercept, so I'm gonna do x-intercept. When x is 0, or no, which one was it? Yeah, y-intercept actually, when x is 0. Because placing a number is easier than finding a number. So place 0, 0 minus 1, minus 1. E to the minus 1 is nothing but 1 over e. Minus here and minus 1. So all I did was just place 0 in here. This is approximately, I believe, minus 1.3, something around that. 373, anyways, so yeah, we found our y-intercept, which is when you have x as 0 intercept. So let's graph. And like this, our horizontal asymptote. And yeah, so we said it hits minus 1.37 in the y-axis, y-intercept. So this is roughly minus 1.37, because this is minus 1 already, so this is kind of like 0.37. So it goes something like this, like that, and you know, like just like that, just connected, no matter how it looks like. So yeah, we're gonna do the range, the inverse, and the sketch of the curve. So the range first. Let's do the reverse engineering method I just talked about in the previous one. So e to the x is greater than 0. Really, anything you mess around with this is not going to affect the range. So minus 3x, again greater than 0. You can think of it as multiplying exponents is nothing but, I mean, oh yeah, it's multiplying exponents. I thought it was addition, so I would have showed you that if you separate the things, it won't matter as much. And yeah. But anyways, it's not going to affect. It's e to the something, so anything that goes in here, be it minus infinity or plus infinity or anything in between, is gonna always give you a positive answer, because e to the no matter what, because this is just a bigger x, you could say, e to the no matter what is gonna remain positive. So yeah, and yeah, so the range is just y greater than 0. If you want to write it the fancy way, then sure, 0 horizontal asymptote, so you can never touch it, so open, and plus infinity. Yeah, so inverse, just do y equals e to the minus 3x. So operate ln, so ln y equals minus 3x, divide by minus 3, so x equals to ln y over minus 3. And so y is, when you interchange, ln x over minus 3. And yep, we're done. So now the sketch of the inverse. So domain, ln is restrictive. Domain of x must be greater than 0. Because it's restrictive. Ln of a number, the number must be positive. Not 0, not negative. Range, we can do this step by step. Ln's range is, ln looks like this, from minus infinity to plus infinity. Dividing by minus 3 does nothing. I mean, does nothing to the range. It doesn't limit it, doesn't somehow cut it or something. No. So yeah, so ln x over that, it's, as I said, it's like from minus infinity to plus infinity, over minus 3 doesn't affect it. So if you write it, you can write it like this, or can just r, so yeah, something like that belongs to r. Anyways, yeah, That's the first one. Second is the behavior. So as x approaches, I only have that. So I can do 0 and I can do plus infinity. I cannot do minus infinity because I'm restricted to plus greater than. So yeah. So as this approaches 0, we can figure it out. If this approaches 0, with ln, the entire expression approaches minus infinity. Minus over minus becomes plus, and infinity over 3 is just infinity, so plus infinity. With this one, put plus infinity, it's just gonna go to plus infinity. So plus infinity over minus infinity over 3 is just infinity, so minus infinity. And okay, 3 derivative. I mean, maybe we don't even need it, I think. Who knows? Let's just derive. So 1 over minus 3x. Derive that again. So drop the minus, so 1 over 3, and then x squared, because you subtract from the power. I mean, if it's down, you add the power, because it's minus 1, subtract, so yeah. Anyway, so now we got the derivatives. This shows us, I mean, this one's easier. This one shows us, this x is always positive. I mean, x doesn't have to be, but x squared is going to always give us a positive number. And so this is concave up, always. We said x is positive. We said x is positive. If x is positive, always positive, then times this negative is going to be always negative. So it's always negative. If you want to phrase it this way or that way, I was going to merge the two words. So for x greater than 0, which is what we're restricted with. Yeah. So that means less than, right? Less than. So it's always decreasing. Always decreasing with a concave up shape. For y-intercept and stuff, just to help us. Anything special with ln? Yeah, if you do ln e. Yeah, if you do ln e, if you say have x to be e, which is 2.7 blah blah, 2.73 I think, 2.771, whatever it is. If you put e, you're gonna get ln e, which is 1 over minus 3. So you're gonna get minus 1 over 3. Just gives us a slight indication. That's nearly minus 0.333. And yeah, so let's start graphing. You can pick more points. You can pick which one did I do? I did when x is 0, so y-intercept. You can do, oh no, I didn't even do that. I just did when this is e, because I can't do when x is 0 because ln is restrictive. So I have to find something else when y is 0, and it's not going to be nice solving for that. I think it's 1. No, if this is 0, then 0 times this 0. So let's ln 1. So 1. Yeah. So if x is, no, we were finding what is x when y is. If y is 0, x is 1. Why? Because if you put 0 here, 0 times minus 3 is 0 equals ln of that. The only value of ln that gives you, or like the value of x in ln that gives you 0 is 1. Ln of 1 is 0. So we got 2 points, 2 nice points, and let's plot them. So minus, so 2.7 blah blah. Wait, let me figure it out. Let me figure out how, what exactly e is. 2.712, 2.72, 718, so 72. Yeah, so 1, 2, 2.7, so somewhere around here. Oh no, minus 0.333, so somewhere around here. And then when x is 1, y is 0. Okay, so you can see where this is going. And it's always decreasing. So we can see that it's decreasing. And it's concave up. And x is always greater than 0. So it's like this. Not a good graph, but this is showing you how a good grasp of how it kind of looks like. If we move this point slightly, I think it'll be better fit here. So it's going to be something like this. So like that. That's the graph of this function. So number 3, parts A and B. So for this one, let's do let u. Otherwise, you can just immediately divide by the derivative. The derivative is 1 over 2 square root of x, divide by that, which means dividing by a fraction such that you multiply by its reciprocal. So 2 square root of x, these will cancel, and so you'll immediately get, no, actually when we do this procedure, we integrate immediately. So you'd immediately get 2 times 5 to the power of this over ln of 5 from 1 till 4. But if you want, I'll do this step by step using the let u. So let u equals the square root of 5. Du, you can do du over dx, or can just say immediately du because that's what we want. But if it's complicated or confusing, then you can do this. Du over dx equals, derive this, so 2 over, this is x. So yeah, 1 over 2 square root of x, and just replace now. So integral from 1 to 4, 5 to the power of u over square root of x times this. Oh, I didn't do the cross multiplication. Yeah. Here what you're gonna do is dx equals, because you want to substitute the dx in. So dx equals, this goes here and this goes there. So this becomes up there. So 2 square root of x times du. And so it's gonna be times 2 square root of x times du. This will cancel with this. You'll have 2. And so 2 outside. Integration from 1 to 4 of 5 to the u du. With something other than e will remain the same, because you actually have divided by ln e, which is 1. Here you're going to divide by ln 5. So 5 to the 5 to the u. In this case, I'm going to replace u again instantly for me. That's how I do it. You can keep u, but you have to change these. You have to substitute into u. So 4, you get 2, 1, you get 1. Yeah. So over ln 5 from 1 to 4. So let's do this immediately. 2 times. I'm going to take the ln 5 outside because it's a constant. Just for me, less calculations to do. I don't have to do ln over 5 again. I mean ln 5 again and again. So yeah. So 5 to the power of 4, square root of 4, so 5 to the power of 2, so 25, minus 5 to the power of 1, which is 5. So you're going to get 20 here. And 20 times this is going to give you eventually 40 over ln 5, which is our final answer for part A. For B, we're going to do the same thing. Let u equals 1 over x. I'm going to pick the exponent. And du over dx is nothing but 1 over x squared minus here. Because, you know, I subtract by, if you bring it up, you subtract by 1. First of all, you drop the exponent, you subtract by 1, and yeah. So dx, because we want to substitute that in, equals, this goes there, this goes there, so you're actually going to do the same one, you're going to multiply, so minus x squared times du. And let's write the rest here. So let me change the color so that you don't, so that you don't mix up with the other one. We're going to change colors. So delete, change the color to blue. I forgot which blue I picked. I think I picked, I mean, I can write in that blue and then switch here. So yeah, so let's continue. So this is nothing now but the integral of 2 to the u over x squared times minus x squared times du. So this cancels with this, and now this is equal to, let me bring it over here. So this is now nothing but 2 to the u with a minus, so minus outside, 2 to the u du. So it's nothing but 2 to the u. I will replace u, especially that this is lagging. It's indefinite, so I must substitute. So 1 over x over, as we said, always divide by the ln. If you derive, you multiply by the ln. So ln 2. And again, it's indefinite, so I can't do anything else. But don't forget your c. So it's going to be this eventually. Well, not eventually, but yeah. So yeah. So for this one, for number 4, you have a rule for log. You can just immediately, it's like len, except with a base that's significant, unlike len where you have log e, which is insignificant, because when you do len e you're gonna get 1, so it doesn't matter. But there's a rule for it, so you can put the derivative up just like the len, derivative up, so 2x plus 2, the function down, so x squared plus 2x minus 1. Now this is the special thing with log, other than e, log e, which is len, you're gonna do len 2 divided by len 2. Another way to do this, which will give you and grant you the same answer, is the change of basis. I can teach you the easy way, which is len of whatever you had. Imagine like someone's holding it and you're gonna be like, don't worry, I'm gonna hold it instead. So the len is now taking its place, but the change of basis, you have to len of the base. So yeah, so imagine they're holding two things, so you're gonna hold it for them. So they're holding the base and they're holding this, so you're gonna hold it for them. So len of this and len of that, and then you can immediately derive. If you notice, you can already see the connection, because I said derivative up, function down, because it's actually gonna be, this is gonna be len, if you derive, len is gonna be or the entire thing is gonna be derivative up 2x. Let me do this quickly. 2x plus 2, len again, as we said, down, and again you're gonna have it's gonna be 1 over, and this is gonna be the derivative up, and so yeah, so you're gonna end up with the same thing, x squared plus 2x minus 1. I just didn't want to write it in that form because it's copy paste, but I'd have actually wanted to write separate to show you that it's the same thing, like this separate. Anyways, it's the same thing, so ignore that. Yeah, okay, so we're doing 5. It's like 4, so y prime equals, divide by the len, so 1 over len 4. If you can't see that, again, log is nothing but when you do change of basis, len of this over len of 4. This is why you have len of 4 down, and it's a constant, so when you do the derivative it remains there, so that's why it's 1 over. Yeah, so this times the derivative up by how's this? Like you put the derivative up, so derivative here, and the function itself, all of this is going to be here. So this is why, because it's a fraction, I'm going to flip the fraction, so the function becomes this. Why? Because it's the derivative. I'm just gonna denote it by, I don't know, let's name this z. The entire thing is z. So log 4 of z is nothing but, the prime of log 4 of z is nothing but 1 over len of 4 times z prime over z. Now what if z is a fraction? I can flip z. So all I'm doing is taking this and flipping it. If you want, I'll keep this for later reference if you want. So yeah, so all I did was flip, because it's 1 over, flip, and the derivative keep the same, like this, x squared plus 1. Also, if you're like, let's say, what am I doing? Also, if you felt like this was kind of like silly and why did I have to do it, you could always skip, because there's always someone who might need this, so I'm always doing it. So yeah, you now simplify, so 1 over len 4 times x squared plus 1 over square root of x. Quotient rule. So derivative of this is going to be 1 over 2 square root of x times the function x squared plus 1 minus the function itself, square root of x, times the derivative of the function, 2x, 2x, over the square of the function. This with this cancels, this is squared by the way, so I'm gonna cancel with the 2 because I'm cancelling one of them because they're squared, so there are 2 of them actually, so I'm cancelling one of them, and I'm gonna do common denominators here, so step by step. 1 over len 4 times 1 over square root of x times, I'm gonna do common denominator, so watch this, 1 this is nothing but 1 over times this, so I'm gonna immediately write it like this: x squared plus 1 over 2 square root of x. I just brought this up here. Minus. Now to do the common denominator, I'm gonna divide by 2 square root of x. So I'm gonna multiply by 2 square root of x. Up. Square root of x and square root of x make you an x. You're multiplying them, so you're making x. 2 with a 2 makes a 4. X with an x makes an x squared. So 4x squared. Let me erase them. And yeah. So let me erase this if you want to see the fraction multiplied. 2 square root of x. So again, square root of x gives you x. X with x gives you x squared. 2 and 2 gives you 4. So 4x squared over 2 square root of x over x squared plus 1. We already cancelled the 2 over there. And yeah, let's keep on going. So 1 over ln 4 times, let me double check something. Okay, so times 1 over square root of x. Again, we can combine. So excuse me. We can combine. So x squared plus 1 minus 4x squared over 2 square root of x over x squared plus 1. These are gonna, yeah. So basically this, I mean, I can simplify the one up, but let's do step by step. So 1 over ln 4. I mean, I can do this a bit faster, but I'm gonna do things step by step, not to confuse it. So minus 3x squared and plus 1 over. Now this is the second step. All I did was simplify. Now second step, this is being divided by this. So this means this is being multiplied by the 1 over x squared plus 1. Eventually making the denominators multiply. So basically I'm combining these two and multiply them. So I'm not gonna multiply them. I'll tell you why. I'm just gonna do this, and you can see why now. Root x times root x is nothing but x, and we're done. We're done. So minus 3x squared plus 1 over ln 4 times 2x times x squared plus 1. Are we done? X squared plus 1, 2x ln 4, and yep, we are done. Double check something. Yep, we're done. Fully correct. So this is not gonna be anything special. This is just gonna be a product rule, but this time you have log, just like any other time, to be honest, in this chapter. So yeah, y prime is equal to the prime of this. I mean, when you have product rule, you have addition in the end, something plus something. So it does not matter which one's primed first and which one's not. It's addition. However, for quotient rule, it's going to be subtraction. This is why you need to know that order. So just get used to it. The first one you see derived times the next one not, and then because you did the one way, you're going to do the opposite way. So derive this minus, derive this minus 1. And this is gonna be copy paste log 1 minus x. I mean, I can do a square bracket if you want, but anyways, plus 1 minus x log of this. Now this is the chapter thing. This is why this is in the chapter in the first place, because of this. So the derivative of that is gonna be derivative up, so minus 1, function down, 1 minus x. What else? Divide by the ln. When you don't say anything, it's by default log 10. It's by default log 10. So ln 10. Anything else? No, shouldn't really be anything. Okay, so we can go straight ahead. So anything special, we can combine anything here. Just place this there, swap with a minus. Nothing special really. Minus log 1 minus x plus, I'm gonna swap these two, x minus 1, because there's a minus, so I just distributed the minus, x minus 1, over ln 10 into 1 minus x. That's it. Okay, so number 7, I'm gonna do some mental math to show you that, to show you which let u to use. But let's first do change of basis. I don't like this log. I want it to become ln. So what I'm gonna do is integral of 1 over x. When you use ln or any other log base, immediately ln off. Immediately use the base or the ln or the log or anyways. So 1 over x over the ln of the base, or if using, let's say, log 10, it's going to be log of the old base, which is 8, and so on and so forth. So ln of 8 and dx. I'm going to get this constant out, ln 8 out here, outside here. And don't do the mistake where you just write ln 8, because there it was in the denominator. So it could be a mistake in copying, like when you copy it, you just write the wrong one. It happens. So just to warn, so that you remember. Yeah, so let's write it out. Ln 8 integral 1 over x. Now, how do you pick which let u to use? Theoretically, if you pick this, its derivative is going to be 1 over x squared minus 1 over x. Minus 1 over x squared. Now that is not going to cancel with this. They don't have the same powers. You're going to be left with an x. So let's try this instead. The function itself. This is the way how you could think before you proceed and then get stuck. So ln of 1 over x. To make things easier for you, let's progress. This is nothing but minus ln of x. Okay, for me the music is a bit too loud, so let me diminish it a bit. I'm listening to Beethoven. Anyways, but in a funny way. Minus ln x, times minus ln x, because I just brought it up, became a minus 1, brought it down, so minus ln x. Now the minus can go outside here, and now we're back to having ln x here. Sheesh. Take the entire frame. Anyways, so dx. Now I'm gonna take ln x. Now you can see why it's useless to take x. Take x, its derivative is 1. You made no change. This is why it's useless. So you should take ln x. Du, this is why simplifications before doing anything is very, very useful. So du dx, 1 over x, dx equals, because that's what we're going to substitute in, x du. Now you can clearly see why it's going to cancel. So minus 1 over ln 8, 1 over x times x times the ln times u. We said it's u times du. This cancels with this. U du, you just square. So minus 1 over ln 8 times u squared over 2, because that's how we do any number, or any variable actually, not number. So x dx is x squared. Is x squared over 2. So u squared over 2, and indefinite, صح? Indefinite. So we're gonna have to substitute back, plus c. So this is nothing but, we picked ln, right? So minus ln of x, all of it squared, right? Ln of x, all of it squared. So take the, this is 1, wait, let me do this, Okay, this might have been a mistake I might have done in my part in one of the notations I've written. As an answer, I got the correct answer, but as a notation, I might have done the wrong thing. So look guys here. You don't, this is ln x squared. Do you do 2 ln x? No, never. Because ln can bring down an exponent on the variable or whatever expression is inside. Once this is outside, this is something else. This is ln times ln. It's not the same as 2 ln. Never. So this is squared outside, up, over ln 8 and 2. So I'm really sorry if I wrote in one of my questions, it's very hard to track down, and if I wrote a notation where I had square up, it must be inside. It must be inside the ln operation or operator, or So 2 ln 8. 2 ln 8 minus ln x squared plus c. And this should be the answer. So